Hi, last time I had demoed the Stanford Research Boxcar Integrator system, mostly focusing on the SR250, which is the fast digitizer and sample system, along with the gate scanner, the SR200. This time I'm going to continue on with a couple of other modules which I have. One is the SR240, which is a fast preamplifier, and the SR255, which is the fast sampler. This demo will show the capabilities of these two units. I don't have a very good setup to actually do some high-speed testing with real waveforms or real application, but I'll create some fast transients and hopefully look at some real signals from AWG that will probably help to demo this capability for both the preamp and the sampler. This is the Stanford Research Boxcar Integrator again, and this time I got a few more modules added. I'm going to talk about the fast sampler over here, which is got a very narrow detection window, which is can be adjusted in 4 steps from 100 picoseconds all the way up to 1 nanosecond, and it's used to capture very short intervals, and of course triggered by external clock, which can go up to 50 kilohertz according to the specs on this instrument, but the actual detection pulse window is going to be very narrow, as you can see, all the way from 100 picoseconds to 1 nanosecond. There's also adjustment to the delay where you want to sample that, just like the SR250, which has got everything on the front panel, but this one has got very few controls on the panel itself. It has to be done through an external supply which is connected to the back, which is a control voltage which moves the delay by 4 steps, which again those are programmed by dip switches on the side of the instrument. I'll go over those specs a little bit later. I don't remember the exact values, but it's in the order of you apply a 0 to 10 volt on the back, and that scales that delay by the dip switch setting, which is I think something like a nanosecond to microsecond in that region. This is really meant for high-speed detection capture windows, and so it's got RF inputs over here, these 3, and one is an out. 2 of these are outputs, one is an input for the signal. The trigger comes in down over here, and below that is the sampled output, which is the A to D converted version of the analog output that is sampled by this narrow pulse, which is set over here. There are also a trigger levels which you can adjust from minus 0.5 to plus 0.01 or plus 1 volt, and these are not adjustable. And the sensitivity is also, you can have 3 settings there. Right now I'm operating in the mid level, which is 0.25 volts, and I've connected the output of this of the sampler, the ADC output, to the digital panel meter on this side, which is common for all the units which can be used to measure in analog form or digital form, as I showed earlier. And so I'm going to show you the signals that I'm actually looking at next. So here we have the same setup as before. I have a signal source which is right now a 50 kilohertz sine wave, 200 millivolts, and I put in an offset so that I could actually make this thing detect around the midpoint. There's some offset in there, I'm not sure why, but I need to maybe it's an adjustable thing in this instrument. So but this sampler itself doesn't have an offset control on the front panel, so unlike the other one, which is the 250, which has got a lot of programmability. But anyway, I've adjusted the offset to minus 80 millivolts and the amplitude of 200 millivolts, and applying that to the signal input from here in channel 1. On channel 2, I'm applying the trigger, which is at 10 kilohertz, the square wave. As you can see, it's 10 kilohertz, 0 to 2 volts. And so on the scope below, I'm looking at the signal output, which is essentially the same signal that is going in but terminated to 50 ohms over here inside the scope. and the actual triggering for this one is based on the sampling pulse, which is the very narrow pulse which I talked about. That is on channel 3 over here, which is the blue trace, and there's a slight small line you can see over there, which is hard to see right now, but that's actually a sample pulse. It's sampling at the 0 degree point, which is also set to the start phase of 0 here, so everything is lined up at the 0 degrees of the sine wave. If I zoom in the x direction, you will see the actual pulse, which is the actual pulse is 100 nanoseconds or so rise time, and there's a decay which is takes about 4 nanoseconds or so. That's the spec actually. As you can see, the waveform is barely visible at this time scale, so I got to go back to fairly slow time window. So right now it's the 10 microseconds, and you can see that pulse is barely visible there. So right now I'm looking at the 0 degree phase. What I'm going to do is to shift the phase coming from the signal generator to 3 different phases to show you what happens, to prove that it's actually sampling at the right location. So right now this is reading 0. I adjusted the offset to make sure this is 0. Now if I go to 90 degrees, actually let's do 180 degrees, and you expect that should be also 0. So I'm going to 180 degrees right now. So the waveform now is 180 degrees. So I can see it's on the falling edge over here, and it should be reading 0 because it's again a 0 crossing at that point, but it's slightly off. The offset is probably not quite correct, but it's close enough for this demo. If I go to 90, you should see the maximum value. You can see this is 0.35 volts, and there's a scaling factor in there, but this is plus 0.35, which makes sense. And then if I do 270 degrees, you should go negative, and so it's minus 0.45. So it's a little bit of offset in that, can be adjusted by moving the signal coming in, but you can see that it's actually working in sampling the right location. Now I'm going to add noise, the same noise I added earlier in one of my previous experiments, to show you it will of course reject the noise. So channel 1 I'm adding noise, and as you can see it makes no difference to the instrument. Okay, noise off, minus 0.46, and let's go to 0 phase again. Okay, that is the 0 phase, and now it's back to minus 0.04, and 180 degrees, minus 0.06. So there's a bit of drift here, but I think it proves the point that it's sampling at the right location. So I set up an experiment to look at one of the internal nodes on the delay generator, and the green curve over here is actually one of the settings on the delay control, which is a capacitively loaded node which feeds the final stage of the delay generator or the trigger generator. So as you can see, this voltage rises depending on, and the speed of this, the way it rises depends on the capacitance that is set on the delay control. Right now it's set at the one of the midpoint positions, I think 100 nanoseconds per division or per volt, and so right now I apply 10 volts to the control voltage, so it should give about a microsecond of delay, 10 times 1 nanosecond, 100 nanoseconds, so that's about a microsecond. So if I now change that control voltage to 0, it should change the shape of this curve. As you can see now, I reduced it to 0 volts, and it's dropped significantly in amplitude, and this will correspond to a certain delay in the delay generation circuit for the trigger. And putting it back to 10 volts, you can see it now goes to a much larger voltage. So it takes time to charge that voltage on the internal node that drives the final stage of the trigger generator. Now to prove that, I'm going to look at right now you can see that the blue curve is actually the trigger, which is at the 100 picosecond trigger which I initially applied, and that position is located with markers on this one. So let's look at that in some detail. Okay, so this is at the 10 volt 0 volt position, and I'm going to switch it to 10 volts, and this is the red curve is actually the trigger, which is coming from this generator on top, which is my AWG at 10 kilohertz. Is looking at the rising portion of this waveform. If I now change this to 10 volts, you can see the trigger has moved about. The delta T between this node and these two markers is about 917 nanoseconds, or almost a microsecond. So switching between 0 volts and 10 volts on the control causes the delay on the trigger, where the 100 picosecond window opens, is moving by about a microsecond, or a little bit less than that. So that's very clearly seen in this demonstration. So I believe that the circuit is working correctly. I was initially thinking it wasn't, so I'm glad to see that this module is totally functional as far as I'm concerned. For the final demo in this video, we're going to look at a fairly complicated looking waveform. It's a pattern that is used to test, I believe, some Ethernet traffic or something like that. Anyway, this is a fairly long waveform. I'm just showing the early part of it, starting over here at 0. If you look at the whole thing, it'll actually look like this. It takes about 25 microseconds and then it repeats itself. There's a lot of activity here. I'm just looking at the early part of this waveform over here. So if you go back to the beginning and zoom in here, you'll see that I'm going to be focusing on this few very small noise components, or noisy part of this, before the first negative transition. So we look at that. So before I do that, I'm going to actually use the SR240 preamp module, which I haven't shown so far. So the signal is 200 millivolts, or sorry, 100 millivolts peak to peak, entering the SR240, which is the module over here to the left of the fast sampler. So the input is coming in on this first top input, BNC, and then it's going out on this black BNC to the signal input of the fast sampler. The fast sampler output, which is basically the same signal, is then I'm showing it on the scope over here on top, and that is the yellow waveform. It's been amplified by a factor of 4. This preamp has this preamp over here has an amplification of 5, but I'm only seeing 4. I'm not sure why. There are 4 channels in this one, and actually all of them show the same gain. So I'm not sure there's a systematic gain error or something else. Anyhow, we still have some decent amount of gain coming into which this is a signal being shown on the scope. I will apply it, of course, to the I'm also applying it to the fast sampler here. The trigger is coming off the AWG on the left, and it's going into the trigger BNC at the bottom below, right over here, and the output, which is the DC output, which is A to D and B to A, comes into the digital display there, and the blue signal over here is our gating signal, or the pulse that is measuring the signal at this point over here. So that's the waveform there. So now it's stationary and there's no scanning going on. So what I would like to do is to show you the actual amplitude at this point. You can see it's measured 0.48 volts, and I'm going to now turn on some noise on this thing. The real use of this instrument is under noisy conditions. If you have a clean waveform, you don't need it. I mean, you can actually see the amplitude there and actually zoom in and measure it. But when you have a lot of noise and you can't even see the waveform in question, then you have to use an instrument like this to find that signal in the presence of noise. So let's turn on the noise, and that's the noise turned on. It's totally overwhelmed by the noise in this case, since it's only 100 millivolts and the noise level is fairly high at this setting. But you can see that the output on the digital meter is still around 0.48, which is the value we saw without the noise. So let's go back, turn off the noise. Now the noise is going to be turned off. It's clean, and if you look at the signal there on the digital output, it's still minus 0.48. That shows the Boxcar pretty much rejects everything because of this extremely narrow sampling window, and the noise that is coming in is totally uncorrelated with that small portion of the waveform, which is always constant at that point. So it's going to only find that as you average it over multiple samples. In this case, there's no averaging, but the fact is that there's a time invariant that particular point in the signal with respect to the gating pulse, which is synchronous to this long waveform. Okay, so now I can see the scanning is turned on, and it's scanning this narrow portion of this long waveform from, it's about a microsecond, I think, from one edge to the other. Actually, it's 100 nanoseconds, I would say. This is 100 nanoseconds per division, so that's 100 nanosecond sweep, roughly. And you will see that the digital waveform output is now varying as a function of time. And if you plot this, of course, you're going to get a faithful reproduction of that yellow waveform in that small interval that we are trying to measure. The reconstruction of the waveform in this small interval of that long waveform I was trying to recapture. What I've done now is applied the X output of the gate scanner, which is the time sweep, to the channel 1 of my scope on top, and I'll show you that. And the output, DC output of the fast sampler, which is going to initially to this DC meter over here, I'm applying it to the Y, or channel 2, and I'm going to do an XY sweep. So now you'll see, as a function of time, the voltage that is being measured over that, for that waveform over that small tiny interval, which is around 100 nanoseconds or so. So this is what it looks like. As you can see, the sweep time is now 3 seconds, which is a fairly fast sweep, because I don't want to pick up too much noise as it's sweeping through. I want to capture the waveform quickly, and as long as I got enough points, I should see a smooth curve, which is what I got over here. And I adjusted the gain as X and Y gain, so I could see this waveform on a much better resolution over here on the screen here. So this is going to be continuously sweeping, and it's in persistence mode of 5 seconds. So it's there's a bit of DC shift going on, but it's fairly small, considering that this portion of the waveform is probably a few millivolts on the original waveform, which is amplified and then sampled by this fast sampler, and then being converted to a digital value and then fed into the scope. So this is a fairly impressive result for a very quick and dirty demonstration of a signal that can be captured. And if you want to do any specific, if you want to capture specific information of a waveform that is repetitive, you can actually use this instrument to do that very easily. So back to the time domain value for the signal that we were measuring with along with this gating pulse. I should probably check the bandwidth limit, make it full bandwidth here, since we are dealing with the full frequency information here, high frequency information. and channel 2, same thing. So what we were looking at was really between here and here, and it seems like that was exactly what we saw on the XY sweep. So this you can see is at the moment 200 millivolts per division, so it's about 400 millivolts peak to peak after some gain, and before the gain it would be probably in the order of 120 to 130 millivolts peak to peak, this whole waveform that is coming out of the AWG. And so this portion of the waveform is fairly small, and it's been it can probably do even better than this if I decided to cascade more stages to get more gain. In summary, I demoed the SR240 fast preamp, which has a 350 MHz minus 3 dB bandwidth, driving 50 ohms. It also has a fixed gain of 5 or 14 dB in each of the 4 submodules. Also demoed the SR255, the fast sampler, which has a fixed pulse width gates of 100 pico, 200 pico, 500 pico, and 1 nanosecond. This complements the SR250, which goes down to a minimum gate width of 1 nanosecond. The SR255 also has only fixed sensitivities of 0.1, 0.25, and 1 volt. The 250 has more settings, like 8 of them, along with offset controls, filter, and coupling modes. The 255 has coarse adjustable delay settings of 1 nanoseconds per volt and up to 1 microseconds per volt in 4 settings, which can be stretched up to by a factor of 10 using an external 0 to 10 volt, like from a gate scanner like the SR200. While not as flexible as the SR250, the SR255 is a good special purpose sampler which has uses for resolving very narrow parts of an analog waveform down to 100 picosecond gate width. Hopefully you enjoyed this video. See you next time.